Hello everyone, and welcome to today's presentation. I'm excited to have you here as we explore the future of enterprise AI systems. Today, we'll be looking at the 2026 production architecture for enterprise AI systems. This is part of our Enterprise Architecture series, and we'll be delving into the blueprint that will guide AI system development and deployment in the coming years. Over the next few slides, we'll cover key concepts, best practices, and strategic insights to help you prepare for this transformation. So let's get started. Let's talk about why AI systems often fail. One of the biggest issues we face is the presence of single points of failure everywhere. There are no circuit breakers, model fallbacks, or graceful degradation strategies when components fail, which means a small problem can cascade and cause the entire system to go down. Another challenge is the lack of a fallback strategy. We often encounter ingestion bottlenecks, embedding failures, or stale vector stores. When data quality issues arise, they tend to cascade and negatively impact the output quality, making the system unreliable. Poor data pipelines are also a common culprit. Without proper management, API calls can quickly drain budgets. There's no rate limiting, caching, or clear cost attribution per request, which makes it hard to control expenses or optimize performance. We also face the problem of missing observability. Without visibility into token costs, latency spikes, or error patterns, we're basically flying blind in production environments. This lack of insight makes troubleshooting and optimization much more difficult. And finally, many systems built for DMOS tend to collapse under production load. They lack horizontal scaling patterns and microservices design, which are essential for handling real-world traffic and ensuring resilience. All these factors combined highlight the critical importance of building robust, scalable, and observable AI systems. Let's walk through the architecture overview, focusing on how the system processes a user request from start to finish. When a user submits a request, it enters through the entry point, which is managed by the API gateway. This gateway acts as the gatekeeper, routing the request into the system efficiently and securely. Once the request is received, it moves into the orchestration layer. This layer is responsible for coordinating the different components, ensuring that each part works together seamlessly. Think of it as the conductor of an orchestra, making sure all the sections are in sync. Next, the request may need some background knowledge, which is where the knowledge base comes into play. The system retrieves relevant information using the retrieval mechanism, often called RAG, Retrieval-Augmented Generation. This process taps into the vector database and embedding store to find pertinent data quickly, enhancing the system's understanding and response accuracy. The core of the language model itself resides in the LLM layer, which generates the response based on all the retrieved information and the user's query. Sometimes, to handle complex tasks or multi-step processes, the system uses LangGraph or agents to manage workflows intelligently. Throughout this process, the security layer ensures that all data and interactions are protected, maintaining user trust and compliance. And finally, the response is sent back through the API gateway, closing the loop and delivering the answer to the user. This flow illustrates how each component plays a vital role in delivering a fast, accurate, and secure system, integrating data retrieval, language understanding, and orchestration into a cohesive architecture. Let's dive into how our API gateway manages security and traffic control. First, we have the rate limit and auth check features, which are essential for ensuring that our system remains stable and secure. When a client makes a request, it passes through the API gateway, which acts as the first line of defense and control point. The request flow begins here, guiding the request from the client through various checks and balances. We also implement request and response audit trails, providing a detailed record of all interactions for troubleshooting and compliance. Comprehensive logging further enhances our ability to monitor and analyze API activity effectively. To ensure data integrity, we utilize JSON schemas and input sanitization, which help validate incoming data and prevent malicious inputs. Request validation is another critical step, where we check that the request meets all necessary criteria before processing. For controlling the number of requests from each client, we use token buckets and request quotas per client. This prevents any one user from overwhelming the system, ensuring fair access for everyone. Rate limiting and throttling techniques, including JWT tokens, API keys, and OAuth 2 flow, are employed to enforce these limits dynamically. Authentication and authorization are at the core of our security layer, verifying user identities and their permissions. The security and access control layer integrates all these components, providing a robust shield around our API. Finally, remember that the API gateway is structured in layers, with Layer 1 being the initial point where these security and traffic management measures are implemented, making it the critical foundation of our overall security architecture. Let's take a closer look at Layer 2, which is all about how we manage the flow of conversations and interactions within the system. First, we have LangGraph and LangChain. These tools are essential because they maintain the conversation context and workflow state across multiple interactions, ensuring continuity and coherence. This means the system remembers what was said before and can build on it seamlessly. Next, we have the state management component, which acts as the backbone for tracking all this information. It helps keep everything organized so that the right responses are generated at the right time. Then there's the standardized tool calling interface. Think of this as a universal connector that allows the system to interact smoothly with external APIs and services. It simplifies how tools are integrated, making the entire process more efficient. Moving on, query classification is a crucial part of the system. It routes incoming queries to specialized agents based on the user's intent and the context. For example, if a query is about booking a flight, it directs that request to an agent trained specifically for travel arrangements. This intelligent routing ensures that each request is handled by the most appropriate agent, improving both accuracy and efficiency. In this setup, we have multiple agents like Agent A and Agent B, working together under the coordination of the router, which uses context tracking and intent classification to decide where each query should go. All of this is orchestrated by the AI orchestration layer, which makes sure that the agents work harmoniously, delivering a smooth and coherent user experience. In essence, Layer 2 is about creating a smart, organized system that manages complex interactions effortlessly, keeping everything aligned with our overall goal of delivering intelligent, context-aware responses. All right, let's dive into the concept of context injection. This is all about enhancing our system's understanding by adding relevant background or supplementary information, which helps improve the accuracy of our responses. When we talk about augmenting data, we're essentially enriching our input to make search and retrieval more effective. Semantic search plays a crucial role here, as it allows us to find results based on meaning rather than just keywords. This is where similarity comes into play, measuring how closely related different pieces of data are. To do this effectively, we generate vectors, which are numerical representations of text, through a process called embedding. Embeddings capture the essence of the content in a way that machines can understand. Now, think of the document pipeline as a flow that takes raw source material, like documents, and processes it through ingestion, where we input the data. Then, by creating embeddings, we transform this data into a form suitable for search and retrieval. The core idea is that when a query is made, it's also embedded into the same vector space, allowing us to compare it against our stored vectors. This is where the embedding index and vector store come into play. They serve as the database that holds all our embedded vectors, organized efficiently so we can quickly find the most relevant chunks or segments of source material. These chunks, or segments, are smaller parts of larger documents, and breaking content into chunks improves retrieval accuracy. Finally, this entire process leads into what we call the Retrieval-Augmented Generation pipeline, or RAG system. It combines retrieval of relevant source material with generation of responses, making our system smarter and more context-aware. Layer 3 here signifies that this is an advanced stage, building on earlier layers to deliver more precise and relevant outputs. By connecting all these pieces, we create a powerful system that leverages context injection, semantic search, and vector similarity to deliver richer, more accurate information. This aligns perfectly with our overall goal of making AI more intuitive and helpful. Now, let's look at some of the key technologies powering our vector search capabilities. We've got Chroma, FAISS, Azure AI, and Pinecone, each offering unique strengths for managing high-dimensional embeddings. Here, you can see examples of document vectors, like Document 1, Document 2, and Document 3, represented as arrays of numbers. These are what we call embedding vectors, which capture the semantic meaning of the content in a numerical form. The core idea is cosine similarity search. This measures the angle between vectors to determine how closely related they are semantically. Think of it as finding the most relevant documents based on their vector proximity, which is much more nuanced than keyword matching. We also incorporate hybrid search features, combining vector similarity with tags, dates, and categories, allowing for more refined and context-aware results. Metadata filters help us narrow down searches further by applying specific criteria. To handle large-scale enterprise workloads efficiently, sharding and replication are crucial, ensuring data is distributed and resilient. Horizontal scaling allows us to grow seamlessly as our data and demand increase. For speed, we use approximate nearest neighbor, or ANN, search, which delivers near-instant results even with millions of vectors. These vectors typically have dimensions ranging from 768 to 1536, enabling us to encode complex semantic nuances effectively. Finally, high-dimensional embedding storage ensures that these vectors are stored and managed efficiently within the vector store, forming the backbone of our layered search architecture. All of these elements work together to provide fast, relevant, and scalable semantic search solutions. Now, let's take a closer look at the various models we can work with, including GPT-4, Claude, Llama, and Mistral. These are all considered model-agnostic, meaning our system can interact with any of them seamlessly. One of the key features here is the ability to tune parameters like temperature, top P, and max tokens to customize the output according to our specific needs. We also have controls over parameters such as budget limits and usage tracking per request, which helps us stay within our resource allocations. Token controls are another important aspect, allowing us to manage how many tokens are used in each interaction. To ensure reliability, there's an automatic failover system in place. If an error, timeout, or quota limit occurs, the system can automatically switch to a fallback option without interrupting service. We have a tiered fallback strategy. First, auto fallback to a secondary model like Claude 3. If that's unavailable or encounters issues, we move to a tertiary fallback, which could be a local large language model. This layered approach, or intelligent fallback strategy, helps us maintain continuous operation. The primary endpoint is GPT-4, which is our main model, but we're always prepared to switch to other models as needed. This setup ensures that our system remains robust, flexible, and efficient, all while supporting different models and handling unexpected issues smoothly. Let's take a closer look at real-time query patterns per user. This helps us understand how individual users are interacting with our system at any given moment. Tracking this data allows us to optimize performance and improve user experience. Cost attribution is also critical. The system assigns costs based on usage, with a rating of 4 stars indicating a high level of accuracy and reliability. This transparency helps us manage expenses effectively. User feedback plays a vital role in shaping our improvements, and usage dashboards provide a visual overview of how our system is performing across different metrics. Analytics help us identify trends and areas for optimization. When it comes to cost, we see that requests exceeding $100 per hour trigger cost alerts, prompting us to review and adjust as needed. Timeout alerts are set for requests taking longer than 5 seconds, so we can quickly identify performance bottlenecks. Rate alerts monitor the percentage of failed requests, with a threshold of more than 1% failures indicating potential issues. Failure tracking and error monitoring are essential for maintaining system health. We also measure latency across different components. For vector search, latency should be less than 200 milliseconds, for LLM-only operations, under 1.5 seconds, and for end-to-end processes, ideally less than 3 seconds. Our overall performance monitoring aims for latency under 5 seconds, with P99 latency targeted below 2 seconds and P95 latency below 1 second. Token costs per request range from just 2 cents up to 12 cents, which helps us keep an eye on operational expenses. Real-time tracking of token costs ensures we're staying within budget while maintaining performance. All these elements come together within our production monitoring framework, which provides comprehensive observability. Layer 6, in particular, integrates these metrics to give us a holistic view of our system's health and performance, enabling quick detection and resolution of issues. In summary, this slide highlights how we're continuously tracking and optimizing key performance and cost metrics in real time, ensuring our system remains efficient, reliable, and cost-effective as part of our overall observability strategy. Let's take a closer look at some of the key items we need to have in place before going live. First, retry logic with backoff is essential for handling transient errors gracefully, giving our system a better chance to recover without causing disruptions. The circuit breaker pattern is similarly important, as it prevents us from overwhelming services that are experiencing issues, maintaining overall system stability. When it comes to logging, ELK or low-key aggregation helps us centralize logs, making troubleshooting much more straightforward. Alongside that, centralized logs are vital for comprehensive visibility across the entire system. It's also crucial to define network boundaries clearly, ensuring that security is baked into our architecture by limiting access and reducing attack surfaces. Speaking of security, real-time spend monitoring and cost dashboards allow us to keep a close eye on resource usage and expenses, enabling smarter budget management. Content safety filters should be enabled to safeguard users and comply with policies, and guardrails help us establish boundaries for acceptable behavior within the platform. To ensure resilience, we implement a multi-tier fallback strategy, including model fallback options, so our service can continue functioning even if certain components fail. Response caching for common queries helps improve performance and reduce load, making the user experience smoother. A caching layer further enhances this by reducing latency and server load. On the scalability front, horizontal pod scaling, or auto-scaling, is configured to adapt to changing demand, ensuring we maintain performance without over-provisioning. Lastly, before going live, we need to go through our production checklist, making sure all critical items are in place, verifying readiness, and confirming that our environment is fully prepared for deployment. Next, we're going to take a deep dive into the enterprise RAG architecture. So, let's start with the key pillars that support this system. Reliability is central, ensuring that the system operates smoothly around the clock, 24/7, without fail. Scalability is also crucial, represented here by the infinity symbol, meaning the architecture is designed to grow and adapt seamlessly as demands increase. Now, looking at the core layers, there are 6 fundamental components that make up this architecture. These layers work together to deliver a robust, observable, and secure system. Observability is about monitoring the entire system, allowing us to track performance and troubleshoot issues proactively. Moving on, at the heart of the architecture, we have the model layer, which utilizes large language models, or LLMs, to process and generate information. This is integrated into the RAG system, Retrieval-Augmented Generation, which combines retrieval of relevant data with generation capabilities, making responses more accurate and context-aware. The agent layer is responsible for orchestrating these processes, coordinating retrieval, generation, and other tasks efficiently. Security is woven throughout the security layer, ensuring data protection and compliance at every level. Finally, at the architecture recap, we see how all these elements come together, emphasizing the importance of a cohesive, resilient, and scalable framework. This summary ties back to our overall theme of building intelligent, reliable enterprise solutions that can adapt and grow with your needs. Let's wrap up with some key takeaways for 2026. Building credibility is fundamental. It's the goal we want to achieve in our enterprise architecture initiatives. Remember, credibility doesn't happen overnight. It's the result of consistent, reliable actions. Showing systems thinking is crucial because it helps us see the bigger picture, understand how different parts of our organization connect, and make smarter decisions. Teaching architecture is about sharing knowledge and fostering a culture where everyone understands the principles that guide our technology and processes. When we combine these elements, building credibility, demonstrating systems thinking, and teaching architecture, we establish a solid foundation. This foundation enables us to build production-ready AI, which is essential for staying competitive and innovative. Ultimately, credibility is the outcome, systems thinking is the method, and architecture is the foundation that supports our journey towards effective, scalable AI solutions.